by the end of this lecture, you will be able to apply conservation of mass and energy to steady state flow problems, which we already practiced in the previous class. We had two examples left to be solved, so I will try to solve those examples by the end of today's lecture. And then also you'll be able to explain the second law, reversible and irreversible processes and Carnot cycles. So reversible and irreversible processes and Carnot cycles, we'll leave it for the next lecture. So you will be able to explain the second law using the statements, Clause's statement and Kelvin-Planck statement. So you will get to know what those are. And also you will be able to calculate the thermal efficiency for heat engines and COP for refrigerators and heat pumps. So this is very important. Like, we are going to introduce ourselves into a new, over the last law of thermodynamics that we are going to cover in this course. Okay, so if you want to expand your knowledge horizon, you can always look into your recommended text and read the recommended chapters. All right. So let's start with example from the winter. If you have ever been to Tim Hortons in a winter day and walk to the EME, think of that walk, right? So Tim Hortons, or if you're going to Starbucks, doesn't matter. Like, let's take, we have a coffee from the Tim Hortons and then we walk towards EME. Then what is likely to happen? Is it going to get cold as we walk, or it's going to get hot as we walk to EME? Any ideas? Cold or hot? It's going to get colder, right? And somebody comes to you and say that, okay, this thing happened, it's a winter day, and now I was walking to the EME and still my coffee get hotter and hotter. Do you think it's possible without any external means? He or she was like just walking to EME and you just get the coffee hot. Yeah, well, that's true. I'm talking about a hot coffee. Like, if it is a hot coffee, let me rectify my question. So if it is a hot coffee, can it get hot any hotter in a winter day as you're walking? It's not possible, right? So, but let's say the person saying, okay, how do you deny my argument? Like, I was walking and then somehow I managed to receive 10 kilojoules of heat. If it is 10 kilojoules, that will be a little too much, probably, I don't know, but 10 kilojoules of heat into my coffee while I was working to EME. So can you disprove this thing? So environment lost 10 kilojoules, coffee received 10 kilojoules. Does this violate the first law of thermodynamics? Does this statement violate the first law of thermodynamics? Environment lost 10 kilojoules and the coffee received 10 kilojoules. Does it violate the first law? It does not violate the first law, right? So now, to prove that the statement made by the person is not happening or not feasible, we cannot just say that, okay, I know that, I feel it, like, it's not the way engineers talk. So we have to back up our statements with theory. So today we'll learn what do we need to back up this kind of the direction process, right? So there's a direction, like, heat cannot go into the coffee in a cold day, rather the heat will be lost from the coffee, so the coffee gets colder. So that's, the direction is very important, but it is not covered with the first law, right? And for an example, another thing, so stirring water increase its temperature, right? We can assume that if we stir it fast enough, we'll have the heat generated, right? And then the generated heat will be lost to the surrounding. Let's assume that we supply that heat back. We supply that heat back to our chamber that we see here in this figure. Oops. Chamber that we see here. We supply that heat again. Then, if we do that, can we rotate the stirrer back? It's true that we can see there's fins and stuff. If we supply the heat, can we get this stirrer to rotate back the same amount, right? So initially we stir the water using the stirrer, and then it generates heat, and some amount of heat is lost to the environment. So then now we stop the process and let it come to the original conditions, and then we supply the heat back, the lost heat back. And do we observe this stirrer rotating? Is my question clear? So let me try again. There's a water cup and we have a stirrer, and I rotate it like this, right? This stirrer, and then the water gets heated because like the water particles are going to move here and there, and it's going to collide against each other, so that it gets heated up and energy is received at the water. And then when the temperature increases, heat is lost to the environment, and that's it. And now I keep the stirrer still and then provide heat. Do I observe the addition of heat can reverse the process? Can it do that? Like it can rotate the stirrer backwards? It cannot, right? Again, this thing cannot be explained by the first law. Why it cannot happen, right? Certain energies cannot be converted into other forms, but it cannot be explained easily by the first law. Not even easily, like we cannot explain it, right? So it's like if we took back some energy, then if we put that back, like we feel like according to first law, it should be totally fine and the system should reverse itself. That's the feeling we get if we are so hung up on the first law. But it's not the truth, right? So now the third example. So in this example, so adding heat to a paddle wheel to the lift weight. Can we do this? Like if we allow the weight to just roll down, and then in that case, heat will be generated inside the box that you see at the bottom left hand corner, right? But if we add the heat to the paddle wheels, can we lift the weight back? Again, the answer is no, right? So now we all see that there's a need for another set of definitions in order for us to understand or explain why these processes are not possible, right? So the first concept that we are going to discuss today is quality of energy, right? It's the quality of energy. Heat is considered to be low quality energy, and work is considered to be high quality energy. How do we qualitatively judge the quality? We can see if a form of energy can be converted into other forms very easily, then we can call it high quality energy, right? You see that work can be easily converted to heat or mechanical power or anything, but can heat be converted to work or anything easily? It is not that easy. If we just provide heat into some system, it does not do what we want. We have to have a mechanism and everything in place, like a relatively complicated mechanism. So such forms of energy we call low quality energy, right? And you can understand this, like work can be converted to heat completely, but the reverse is not true. So you remember when we were stirring the cup that you see here, we were able to convert the work into heat, but we were not able to convert the heat into work that easily, right? So are we getting the idea of this quality of energy? Perfect. So there are other means to calculate the quality of energy, like exergetic efficiency and everything, like the quality of thermal energy. So don't worry about those for right now. But now you get the sense why that cannot happen, right? These processes cannot be reversed as we expect by just supplying the heat that is lost during the process, right? And also by these discussions, we have a very clear idea. A process can only occur in a certain direction, right? So it cannot happen the other way. Like a coffee could not get hot just by walking into EME from Tim Hortons, right? Our walk does not necessarily increase the heat inside the coffee. So it it is supposed to happen in a certain direction. And also, sadly, satisfying the first law does not ensure whether a process can occur. It have been so easy if it was just the first law, right? Then we can just apply the first law and be happy. But satisfying the first law does not ensure whether a process can occur, right? So we need to check furthermore. It's obvious that the first law should be satisfied in order for a process to take place, but that is not the only condition that should be met. Now, let's introduce ourselves into one of the most important components that we are discussing through this course, heat engines, right? If you look into the definition, any continuous operating device that produces work through the transfer of heat from a high temperature body to a low temperature body is considered to be a heat engine, right? A high temperature body is called a heat source, and low temperature body is called a heat sink, right? So source and sink. Now, any turbine, any IC engine, anything that you come across during this course, like any engine that you come across, is going to be falling under this definition, a heat engine, right? So here, down here, you see a steam engine, right? If you look at the process, the working process of this steam engine, let's start at the boiler. Let's start at the boiler, and here we add heat so that we can heat up the water and create steam, right? And then the heated steam comes to the turbine, and it goes through the turbine so that the work can be generated, the shaft work can be generated. Now, as the steam goes through the blade series, then the shaft is rotating at a certain output, right? This many kilowatts. And now, after that, the steam leaves the turbine and enters the condenser. In the condenser, it ejects some heat into the heat sink or surrounding, right? And then it enters to the liquid state so that it goes to that water pump, and the pump pumps it back to the boiler so that the cycle can continue, right? So we heat steam and use it at the turbine, and then we go back to the condenser, and there we condense it, and then we send it to the pump. Pump pushes it back to the boiler, right? So if we define our system boundary as seen here, we can see that there's a heat input QH coming from the energy source, and then there's a work output leaving here, and then some of the heat is rejected to the heat energy sink or heat sink, and then at the pump there's a work input, right? There are 4 components. And then if we apply our first law equation, you can see the system is very small, so you can assume that the potential energy difference of the substance is not significant, and also kinetic energy level is not significant. And then as is a cyclic process, the substance returns to its original state once it goes through a cycle. Assuming steady state conditions, you can come to this point, right? Using the first law, the total amount of heat added into the system is equal to the total work output or net work output. We agree with this statement. Now, to write the Q net in, right? Q net in is QH minus QL. The amount of heat coming into the system is added as a positive component, right? and then we subtract the amount of heat leaving the system. This thing we agreed even in the first law applications for the closed systems, right? And then similarly, W net out. So we can say that work done by the system is W out, and minus work input to the system is added as a minus component, or like we subtract the number, right? So this way we make sure that our first law components are quantified, right? For an example, let's say, so we say that this turbine can generate 10 kilowatts, right? And then work input is 1 kilowatt. And then somebody says this is the steam boiler, added QH 11 kilowatts, right? So how much heat would be rejected to hit its heat sink? So this would be our question now, right? So there, what we can do is we can take QH, we can take W out, which is 10 kilowatt, and we can subtract the work input 1 kilowatt. This is going to be, let's say, 10 and 1, 10 minus 1, right? So it's going to be 9. And we know that from the first law, Q net is equal to W net. Therefore, we know that Q net is 9, right? So our QH is given. So we need to find what is QL. See that how we plug in the numbers. So this is why we need these relationships, right? Now we can quantify the heat inflows and outflows if we know some other components, or like some of the heat and work outputs. Then we can calculate the missing components. Okay, so now we are there. Then the other thing that usually people are interested is the thermal efficiency, right? This is a big discussion when we try to evaluate a system. We would like to ask, okay, what is the efficiency of this engine, or what is the efficiency of this system, right? So the definition of efficiency is the net work output divided by total energy input, right? So here the net work output is W net out, as the name implies. And then what is the energy input? It is going to be QH, right? So don't mislead yourselves like thinking that it's Q net, because sometimes students tend to like mix these things up. W net out divided by Q net in Q net, then it's going to be 1 always, because W net is equal to Q net, right? From here, it's just the heat input. QL is not something we provide. It's a heat loss to the surrounding, right? It's a loss. So that is the one that creates the inefficiencies. So now from this first law equation, we know that Q net is equal to W net. So in other words, we can use Q net equation to represent W net here, right? So that means thermal efficiency is equal to QH minus QL divided by QH. QH minus QL divided by QH, right? So then we can end up coming here. We discussed about the heat engines. Now the other important device that we are going to discuss in this course is refrigerators. Again, refrigerators are cyclic devices, right? Let's go through the definition together. So a cyclic device which absorbs heat from low temperature body, right, and rejects heat into a high temperature body by consuming work, right? So now, what is the use of a refrigerator? What are we trying to do? What are we trying to do with this one? What is our goal with the refrigerator? We are trying to cool food or things inside the refrigerator, right? That's our goal. So that means our desired requirement is the cooling effect that we receive, right? Okay, so let's see how this works, right? So evaporator absorbs heat from your refrigerated space. So this is where refrigerated space is where we absorb our heat, right? Or where we store our food and beverages and stuff. And then it goes through the compressor, right? After you are absorbing the refrigerated heat from the refrigerated space, this refrigerant becomes vapor, right? And this vapor is sent to the compressor, and then this compressor compresses the vapor and increases the pressure and temperature of the substance, and then send it to the condenser. At the condenser, we eject heat to the outer surroundings. In this case, in your practical reality, the refrigerators are usually located at our kitchens. So this outer surrounding is the kitchen, right? And then after doing that, after removing heat, then we send it to the expansion valve. And as we learned the other day, what an expansion valve does is a pressure drop without enthalpy change, right? And then there we drop the pressure and we go again to the original conditions which we started, and then the cycle continues throughout, right? If you have seen in certain refrigerators, especially older models, like if you go behind the refrigerator, you may see something like this with a tube with some wires like this. Anybody have seen such a thing behind the refrigerator? Perfect. So this is your condenser coil, right? This is what ejects the heat to the outer surrounding or to your kitchen, right? And have you ever heard that you should not put your refrigerators very close to the wall? You should have like about 1 foot or some distance from the wall. Have you heard that? Perfect. So now you see why it is, right? Because if we keep it so close to the wall, then there's a thin air layer and which is trapped in this gap. And once we heat it, the temperature of that gap increases and it makes it harder and harder for the refrigerant to eject heat, right? In newer models also they use the same cycle, but it is not as visible as in older models. That's the thing, right? So if we make it so close to the wall, then we cannot effectively transfer heat because we heat up the local air layer around this condenser. So if we increase the gap, so that allows the air to be circulated, right? So then the heat transfer is more effective because the local air is getting circulated. So we have more potential to eject heat as the air is not getting heated up locally, right? The same principle applies to baseboard heaters. Have you ever heard that you should not press your couch against the baseboard heater? Anybody? That's the same idea, right? Even though we do not cover baseboards in our course, the same thing. Baseboards are used to heat your space. So if you just trap it, like if you just put a couch around it, then the air cannot circulate. So then it just heat up the local air, and it keeps doing that, but your space is not going to be heated as effectively. Eventually it will heat, but a lot of heat will be trapped behind your couch. That's why people say that you should not block the airflow to a baseboard, right? And the other thing, so the other thing that is very noticeable in certain refrigerators is the noise from the compressor. Some of you may have heard there's a humming noise coming in the refrigerator at certain times. Have you noticed that? It's not always continuous. If it is continuous, there's something wrong. Like at times it pops up the noise, and then it becomes quiet. Have you noticed that? Anybody? Perfect. So that means what happens there is, so let's say we want to cool our food to 5 Celsius, right? In engineering, we cannot exactly say that, okay, 5 Celsius and 5 Celsius it is. So what happens is we set our maximum temperature inside the refrigerated space into 5 Celsius. And then we say that, okay, so keep it below 5 Celsius. Whenever we are trying to go above 5 Celsius, whenever we are trying to go above 5 Celsius, then the refrigeration cycle activates. Then it keeps on cooling the space, removing heat from the space, so that, let's say, to another threshold level, lower bound, something like 4 Celsius, right? After that, after we reach 4 Celsius, then refrigeration system stops working. Now it allows the space to be as is, and then with time again, the temperature slowly tries to go beyond 5 Celsius, right? So then again the refrigeration system activates. Then when the refrigeration system is in working order, compressor is the one that has the moving parts, right? So that's what makes that noise, the humming noise, right? So that is a bit of background about how the refrigerators work. I tend to explain that because it's closer to your realities. So let's go back to our analysis of the system, right? Now you can see in this refrigerator we add work to the compressor, right? We add work to the compressor, and then also, like, our required effect is refrigeration effect, like we absorb heat from the bottom or refrigerator space, right? And then we eject heat to your kitchen or surrounding, right? Now if we apply the first law similar to heat engines, we can say that net heat is equal to net work, or else, so we can say that QH minus QL equals W net in, or we can say that QH equals QL plus W net in. So are we all clear about the first law expression that we use here? Perfect. Now we would like to compare our refrigerator with our neighbor's refrigerator and say that, okay, I've got an efficient one, right? So if you want to do that, you need some means to compare your refrigerator with your neighbor's one, right? To do that, you need to define an efficiency parameter. So in efficiency, what do you mean as the top part? The desired output, right? Or the desired effect that we are waiting to receive, and then divided by required energy input. This is the general form of efficiency, right? In this case, what is our required output? It's the cooling effect, right? It's the cooling effect. So in this case, QL divided by W net. W net is the energy input, like given to your compressor by your electrical socket, and then QL is the heat, amount of heat that is removed from your refrigerator space. right? And then we can say that W net is equal to QH minus QL, and then we can come to this final expression, right? Yes, heat in is positive, heat out is negative. So let's say if we had 5 and 3 here, right? W net in, and here what should it be? So let's say QL is 5, W net in is 3, and then QH is going to be 8, right? Did I answer you, Kylie? Did I answer you? It's positive 8 because W net in, sorry, give me 1 second. No. Like in this case, QH is the scalar value. You know what I mean? QH is the scalar value, right? So QH does not have the directional information. So we have read it before QH or QL, like negative or positive. That's our responsibility. QH, like that is a very important point. QH is a scalar quantity that we mentioned here, QH and everything. Those are scalar values. The signs in front of it, positive or negative, that indicates what we intend by it. Are we clear? Yeah. So like, let's say, let's try to write this like this. So ideally, Q net is equal to W, right? Let's say that, right? So what is the amount of heat rejected to this thing? That is what we are going to find. QH rejected is going to be negative, right? Removed from the system, minus QH plus QL is 5 equals W net is going to be minus 3 because it is done on the system, right? So then now you can see, if you reconfigure the equation, then you can find the value to be 8. QH is 8. Do I make sense? The thing is, like, always think from the inflows and outflows point of view when you're substituting. Don't get carried away by the formulations, because like these are just to understand, right? So if you are not sure which equation to use, always go to the first principles and use your original equation, the basic form of the thermodynamic first law, and then derive it yourself using assumptions and substitute your values. Then nothing will be wrong, right? So now back to our question. Now we can define our efficiency value like this, but there's a catch. Importantly, you see that now we don't call this efficiency anymore. We call it coefficient of performance. Why don't we call it just simply efficiency of the refrigerator, right? We could have just called that. But the thing is, if you look at this value, if you look at the bottom right hand corner here, you can see that if QH over QL, if QH over QL is less than 2 and greater than 1, QH over QL is always greater than 1, because QH is the sum of QL plus W net, right? Therefore, it is always greater than 1. So we know that. But in cases, QH over QL can be less than 2, right? So if it is less than 2, what can you say about this expression? Is it greater than 1 or less than 1? For ease of your analysis, I'll say that QH over QL is equal to 1.5. So what is the value of this expression? What is the value of this expression? Anybody with the answers? It's greater than 1, right? If QH over QL is 1.5, that means 1.5 minus 1 is the bottom component. That means 0.5. 1 divided by 0.5 is 2, right? So that means greater than 1. So in the efficiency point of view, if somebody come to you and say, okay, my system has an efficiency of 200%, would you freak out or not? Would you say, okay, that doesn't seem right? Would you say that, or you say that, oh, it's cool? What would you say? Would you agree with 200% efficiency, or you would say like something is not right there? It's say we all feel it's not right, right? So that's why we do not use the conventional word efficiency in the refrigerators, because refrigerators, like, you can get more cooling effect than the amount of energy that you provide. That's why we use COP as our if performance indicator to evaluate the performance of refrigerators and air conditioners. We don't use efficiency, we say it's coefficient of performance, or COP. Okay, so are we all clear about how do we calculate the COP for refrigerators and all this stuff? Perfect. Now the third important device, I believe that is the last device that we are going to cover under the second law, heat pumps, right? So let's go through the points up there in the slide. A refrigeration system operating in a reverse mode. And it says a heat pump absorbs heat from a cold space and deliver more heat to a warm space by consuming work, right? So basically, you all know what a heat pump does, right? In a winter day, if we have a heat pump, what it does is it absorbs heat from the outer surrounding, and then it ejects heat into our house so that we can be warm and cozy, right? So that's what it does. And in this case, this is almost like the reverse of the refrigeration system. If we go back to the previous slide, you can see if we place our house as the house that needs heating, right? If we place our evaporator outside the house, then what this would be doing is would be absorbing heat from the outside and ejecting it into our house, right? So basically it becomes a heat pump, right? So the purpose is different, but the idea is the same. The purpose is to, in this case, the purpose is to cool a given space, right? And the purpose of a heat pump is to heat a given space, right? And now if we draw a system boundary around our heat pump like this, then we can write our energy balance equation or first law equation like this. It's the same as the previous example, because the flow of energies are the same, only the required or expected outcome is different. In the previous case, our goal was not to heat the kitchen but to cool the refrigerated space, right? In this case, our goal is to heat the house, right? Everybody clear up to this point? Yes, heat pumps are efficient, actually ridiculously. I will explain why. We will come to that point, right? Now, again, to compare your heat pump with your neighbor's heat pump, if you are a competitive person, you want to be efficient than your neighbor, and then you need a performance indicator, right? So to do that, you say, okay, desired output divided by required input, right? So desired output is what? In this case, what is the desired output? Is it QH or QL? Any idea? Desired output is QH, right? Excellent. Because in this case, we are not interested. We are not trying to cool the surrounding. In a winter day, anyway, it would be cruel, right? We are trying to cool the surrounding so that somebody out there in the road is going to feel more heat. No, it's not our goal. Our goal is to heat our house, right? So QH is our desired output, and required input is the input that we give, W net in, the input that we add into our compressor, right? So then, as we did in earlier steps, we can substitute to W net by QH minus QL, and then we end up coming here. And there's an important observation in this last part. What can you say about QL over QH? Is it less than 1 or greater than 1? Is it less than 1 or greater than 1? It is less than 1, right? Always QH higher than QL, because QH, as seen from the first law equation, QL plus W net is the value that we get for QH. Therefore, it's always less than 1. When it is always less than 1, what can we say about this expression? Is it less than 1 or greater than 1? It is always greater than 1, right? Excellent. Because 1 minus something less than 1, it's going to be a decimal point, and 1 divided by a decimal value, then it's going to be always greater than 1. That's why the observation that Kylie mentioned comes into play. The heat pumps are very efficient, because if you add 1 kilojoules of heat, then you can get more than 1 kilojoules. If you add 1 kilojoules of work, then you can get more than 1 kilojoules of heating effect, right? So that's the difference. Like when it comes to natural gas furnaces, they can reach, in hypothetical scenario, maximum case 100% efficiency. So that means in a natural gas furnace, like what we do is electrical or natural gas, both. In a furnace, what we do is we burn something, or we use a coil and we heat the air, right? The maximum we can do is we can give 100% of the energy we input into the device into the air. So that is going to be 1 kilojoules, best case 1 kilojoules of heat, right? But in heat pumps, it's different. If you add 1 kilojoules of heat, then it will output 2 kilojoules of heat or more, like something like that, right? COP is always greater than 1, right? So that's why people say that electric heat pumps are ridiculously efficient, or rather, like they are way effective than the furnaces. But the catch is, here in BC, the natural gas prices are very low, so the efficiency and the cost, that does not reflect the same thing. So heat pumps could be efficient, but natural gas furnaces could be way cheaper. So that's where the people make choices, right? So are we clear about this one up to this point? Perfect. Now, the second law of thermodynamics, this is very important, right? So in second law, what we are trying to say is certain processes cannot act in certain directions, or we cannot reach certain efficiencies of devices. Those kind of things we are going to establish within the scope of the second law. You remember at the very beginning of this course, I mentioned that if somebody comes to your place and says that he or she has a car with 100% efficiency, then you can challenge them, right? You can challenge them. No, you cannot. Like with the second law, you can see how you can challenge them and why you cannot achieve 100% efficiency. Today we will not be discussing that. It will be in the next lecture, but you will have theory to argue there, right? So in the second law, we interpret the second law using two statements. The first statement is, it is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce net amount of work. So you remember from our earlier example about the heat engines, we added heat into the boiler to the steam to generate steam, and then we generated work, and then we ejected some amount of heat into our heat sinks at the condenser, and then we sent it back to the pump, and then pumped it back to the boiler, right? So if we were to interact with one reservoir only, then what it essentially means is that QL becomes 0, right? QL becomes 0 if it is only one reservoir. So we have to definitely work with heat source, because without heat we cannot generate work, definitely, because there should be some form of energy coming into the system. And now if it is the only reservoir that we are dealing with, then it means we cannot eject heat at the condenser, right? So if that is the reality, then we can draw a schematic indicating that this is high temperature reservoir and this is our heat engine, the cyclic device, and then here's our heat input, and there's only work output. If we had QL, then it would have looked like this, right? This is TL and QL, but in this case we don't have a QL, so it looks like this. So are we clear about this schematic up to this point? Like the things we discussed? I'm sorry I'm asking this too many times, but just to make sure that you understand things, right? Because if I explain too many things without you understand the first things I mentioned, that will be tricky. So do you understand up to this point till we draw the diagram? Perfect. Now what Kelvin Planck statement says is, this is not possible. We cannot have such a device. In thermodynamic devices, we cannot have, basically it means we cannot have 100% efficiency. QL was the loss there, right? So QL was the energy loss, but if we can avoid QL, then that means we can have 100% efficiency, or thermal efficiency equals 1, right? 1 or 100%, the same thing, right? This statement says we cannot have that. So the conclusion is thermal efficiency is always less than 1. So in this course, we are not going to discuss the derivation of this statement or anything, but we are going to believe that is true, right? So if somebody says, now somebody comes to your house and say that I have got a IC engine with 100% efficiency, you say that no, check the Kelvin Planck statement, and you cannot have 100% efficiency in your IC engine, right? If it is a thermal engine, you cannot have 100% efficiency. That conclusion comes up here, right? But still, they might say, okay, it's not exactly 100%, it's 98%. Like if it is 98% with this one, we cannot argue further. We can say it's possible or it's not possible, but it's not really possible. So with the theory you get from the next lecture, you can say that, oh no, it's not going to be 98% either, or 90% either. So we'll see how we can argue with that, right? And then this is the Kelvin-Planck statement. Are we all clear about the Kelvin-Planck statement? What it means? Perfect, 100%. Anybody having doubts? Perfect. Now, the second statement that we use in Clausius, in second law, is the Clausius statement. So what does it say? Let's go through it together. It is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from a lower temperature body to higher temperature body. So basically it says that we cannot have a refrigeration device or a heat pump that does this, like absorbs heat from a refrigerated space and eject heat into your kitchen without any work input. If we had such a device, right, if we had such a device, then you would not need to plug your refrigerator. You just bring in the refrigerator from Home Depot or wherever, and then you just place it, and then you are happy ever after. It's cooling your beverages forever, right? So that what the Clausius statement say, unfortunately, you cannot purchase such a machine. There's no such machine. That's what it says, right? So when W equals 0, we can draw the schematic as seen here. QH is ejected and QL is absorbed, right? So if we apply the first law equation here, you can see that QH and QL should be equal to each other under steady state conditions, right? So COP of a refrigerator can be written as QL divided by W net. Then if W net is 0, that means your COP is infinite, right? Infinity. What does this mean? If it is infinite, so for a very little amount of work in, you can get infinite amount of work done or infinite amount of cooling effect. It's like you provide 1 kilojoule. You provide 1 kilojoule to your refrigerator, and then you are good forever. For those who don't understand how ridiculous that is, so it's like you go to Tim Hortons and give $1 one day, and then they say that, okay, this is good enough for the coffee that you are going to consume throughout your entire life, right? So it is always nice if there was a financial model like that, but unfortunately there's not such a thing, right? So similarly, we don't have such a refrigerator which can just get 1 unit of energy and do the work for your entire life, right? And then here, so the conclusion, COP is always less than infinity, so it cannot be infinite, right? And at the same time, W net in cannot be equal to 0, right? So less than infinity is a vague statement. Can COP be 100,000? No, it's not possible. Like we'll see what are the real values or what are the realistic values with the Carnot cycles, right? So to establish the theoretical limits, the same as about example about heat engines. You cannot have heat engines at this efficiency range. How are we going to determine? Using Carnot cycles. And then again, for refrigerators, we are going to establish the theoretical maximums of COP using the Carnot cycles, right? Now let's move on to the next one. So we learned two statements, right? We learned two statements. Kelvin Planck statement and closest statement. So we did not prove any of those, but if we agree with one, you have to agree with the second one, so that we can prove, right? You cannot say that I agree with Kelvin Planck statement, but I don't agree with closest statement. You cannot say that. If you agree with one, you're bound to agree with the second one, right? So let's go through the statement above here. Any device that violates the Kelvin Planck statement also violates the closest statement, and vice versa, right? Okay, let's see. Let's take a heat engine that violates Kelvin Planck statement. If a heat engine violates Kelvin Planck statement, that means it can convert 100% of the thermal energy that it receives to work, right? Basically, there's no QL. There's no QL, right? That is what it means. There's no QL component. Now, heat is absorbed, and 100% of the absorbed heat is converted into our work. Now, the refrigerator, we can use this heat engine as the power source or energy source for our refrigerator, right? To operate our compressor. So we input this compressor, we input this work into the compressor, right? And then refrigeration effect is absorbing heat from a lower temperature reservoir and eject it to a high temperature reservoir. Now, looking at this diagram, you can see that W net is the one that is coming into the refrigerator, and QL is absorbed, and this much heat is ejected. As W net was the amount of energy that we received at the heat engine, and the heat engine operates at the 100% efficiency, therefore the work input into the refrigerator is equal to QH, right? Therefore we can write the total energy ejected by the refrigerator is going to be QH plus QL, as indicated here. Now let's draw our system boundary as this, right? Now this becomes 1 unit, right? We can say that, okay, we have a refrigerator with inbuilt generator whatsoever. Now it becomes 1 unit. So if we simplify the interaction between the high temperature reservoir and our device, it's going to be QH plus QL and there's a QH going in the opposite direction, right? QH received at the device and QH plus QL was ejected by the device. So the net effect is going to be QL ejected by the device. And then again, QL here does not change. It was the amount of energy that we absorb from a low temperature reservoir, right? So now this device that you see in the right hand side can absorb heat from a low temperature reservoir and eject it to high temperature reservoir without any external work, right? So then we can say that it violates the closest statement. Anybody who's not clear what happened, please feel free to ask, because that brings up the questions. If you are not clear, don't hesitate, please ask. Okay, so Alan, do you understand the simplification this point? So if we go back to previous slide, this is what closest statement says. This kind of a device is not possible, right? So in this case also QH is equal to QL, because from the first law, right? Because there's no any other energy flow into the system. And what closest statement says is you cannot have such a device just absorb heat and eject the same amount of heat into a high temperature reservoir. You cannot have such a device, right? And then if you have this device, that means this is a violation of the closest statement, right? So now we have just proved that if we agree with one of the statements, then you have to agree with the other one. There's no way that we can disagree with one and agree with the other. Okay. So now, after going through all this theory, we come across a very important notion. Any device that violates first law or second law um, is called a perpetual motion machine, right? So any device that violates either law is called a perpetual motion machine. So what a perpetual motion machine can look like, so you can go through the bullet points. A perpetual motion machine that violates the first law can produce work from nothing, right? It was like the refrigerator that we don't have to plug in. You just do work, keep on doing work, right? And in the second law, a perpetual motion machine that violates the second law convert 100% of the heat extracted from a source into other forms of energy. You cannot have that either. So you add 100 kilowatts of heat, and you cannot get 100 to a heat engine, and you cannot receive 100% work or 100 kilowatt work from that engine, right? So there's a funny video in YouTube, like if you check perpetual motion machines, like there's a cat and peanut butter and cheese or something, like then the cat turns all the way around. But other than that machine, people have not found a perpetual motion machine yet. Okay, those of you who have not tried this question before, you can take about 3 minutes to try this one, and then we'll all go through it together. Okay, let's go through the solution together. So in this question, it discusses about a steam turbine, right? So, and this is, let's say, inlet, and this go out, and then we have W out, right? And now in the conditions are listed here. In the inlet, it says the mass flow rate is m equals 3 kilograms per second, and then pressure is given P1 or P in equals 1200 kilopascals, and temperature is given T in, which is 350 kilopascals, and velocity is given v1 is equal to 15 meters per second, right? And then the outlet, we have been provided with pressure P exit equals 100 kilopascal, and then temperature T exit equals 150 Celsius. This is, and very low velocity. We can assume that VE is not significant, and we can assume it to be 0. find the specific work and power produced, right? So in this case, we'll start with the base case of the first law, Q minus W plus M1 M in right? So now we are here, and let's apply our assumptions. Assuming steady state conditions, we can say that this is 0, right? And assuming quick operation and adiabatic conditions, we can say this is 0. And W, we cannot of course say 0 because it is something very significant in a turbine. And then enthalpy of the inlet fluid, it cannot be said 0 because that is the one that carries the energy from our heat source, right? So we cannot say that is 0. And V1 was given. Usually in turbines we will neglect V1, but in this question the V1 was given, therefore we will not neglect that. And the potential change difference can be neglected, therefore we'll cancel out GZ1 and GZ2. And exit velocity was said to be negligible, so we can say that it is close to 0. Now you see that we are left with work, inlet enthalpy, inlet velocity, inlet kinetic energy component, and exit enthalpy. Now it's a matter of finding the enthalpies from the property tables and substituting the values. And before substituting, please try and see whether you can find these properties from the property tables, and let me know once you find it, or if you have challenges in finding it. You can use inlet conditions, pressure, temperature is given, outlet pressure, temperature is given, so you have enough parameters to find enthalpies. So after finding H1 and H2, we substitute the values here, right, to find the work done by the turbine. So here, inlet enthalpy, exit enthalpy, that is straightforward. And then here, the V1 squared over 2, and you see there's 1,000 here. We divide the number by 1,000. Why is that? Because here you see the unit is given in kilojoules, right? So if we substitute everything to our velocity component in SI units, what we are getting is joules, not kilojoules, right? So that's why we divide this answer by 1,000 to convert it into kilojoules, right? So you can see this number is going to be 0.1125. So if once you solve this entire expression, you get 0.1125 kilojoules per kilogram. Now 0.1125, so you add that to compare to this number. Is it significant? Compared to this number, is it significant? The final or turbine work compared to turbine work, the energy input by the velocity of the inlet fluid, is it significant? It is not significant. Excellent. So because it's 0.1125 and the total value is 377.3, so it is definitely not significant. That's why we say that in turbines, the inlet velocities and exit velocities are not very significant when we are dealing with the enthalpies involved, right? And to find the total work or the total power output, we just multiply our specific work by the mass flow rate, and then we arrive at 1132 kilowatts, right? So are we all clear about how we arrived at the final answers and the important things like dividing the velocity by 1000, right? Like velocity, specific kinetic energy by 1000 to convert it to kilojoules. If you do not do it in exam, then you will get a very wrong answer. You will get 125, 112 here, and then that will significantly change this number, which is wrong, right? Now let's move on to the second example today. Please take 2-3 minutes to go through this, and then we'll discuss together. Let's go through the solution together. So the inlet conditions given and also exit conditions given. So if we think of the compressor itself, what it does is it compresses the fluid and changes its pressure and temperature, right? So let's try to start from the basic principles. dECV over dt equals Q minus W plus M into H in plus V1 squared over 2 plus GZ1, and then minus M again H2 or H exit plus V exit squared over 2 plus GZ exit, right? So assuming negligible potential energy, we can get rid of these two, and assuming the velocity change is not significant, we can get rid of these two, and assuming adiabatic operation, we can get rid of these two, this one heat, and assuming steady state operation, we can get rid of this one. So basically we are left with W equals M dot H1 minus H2, right? I derived this from the basic principles so that you know how to do it, right? But in case if you want to quickly find it, you can look at your formula sheet. For all these devices, you have the general form using the general assumptions. In the previous case, we had velocity, so in such a situation, you cannot use the equation directly from the formula sheet because it's assuming the velocities are negligible. But in this case, there are no exceptions from the general assumption, so you will find the exact same equation from your formula sheet, right? And then the answer is pretty straightforward. What you have to do is to find enthalpy at inlet and enthalpy at exit. So this should be exit, sorry. And so you go to property tables and locate these two properties and then substitute here, and you will get the specific work, right? So you see the work that you have here is negative, right? Because we derived our first law equation assuming that the work is done by the system, right? So this means like the negative sign indicate that work is done on the system or work is input into the system, right? So that's the solution. If you have any questions about that, I'm happy to answer. But if you don't have any questions regarding this one or something else, feel free to leave. This is the end of the class today.